This is the video that introduces energy. So let's just take a look at like a Nerf gun firing a Nerf dart, right? So Newton's third law tells us that there is a force acting on the dart and on that Nerf gun as well. So which object, that Nerf gun or the dart, exerts a larger force and magnitude to the other object? Newton's third law, opposite equal. Those forces are equal. Force pairs are simultaneous, which means they start at the same time and they're applied for the same amount of time. Now they don't cancel because one's acting on the dart, the other's acting on that Nerf gun. Now, which object experiences a larger impulse? So we've already established that the force applied to each object is the same, and the time interval that force is applied is the same. So you can see here that impulse is the force times the time. So it's going to be the same impulse. Which object experiences a larger change in momentum? Change in momentum is impulse. Impulse is change in momentum. If they each are applied the same impulse, they each experience the same change in momentum. Why is the effects of the same impulse different on the objects? Because that dart has a much smaller mass. So what we've already established is that the force applied to each of these is the same. The time that force is applied is the same, which means the impulse is the same. The change in momentum is the same. But that dart's going to go a lot faster, larger change in velocity because it has a much smaller mass. So let's ask these other ones. What is the total combined momentum of both the Nerf gun and the dart before the dart is fired? It's going to be zero because if you'll notice, both of them, both the Nerf gun and the Nerf dart, are not moving. It's going to be zero. What is the total combined momentum of both Nerf gun and the dart after the launch? How do you know? Well, the momentum after the launch is going to be zero as well because I cannot create or destroy momentum. Whatever momentum I start out with, I have to have the same amount. So how this works is because momentum is a vector quantity. Whatever momentum is going forward with the dart has to balance out with the momentum going backwards with that Nerf gun. Now, what could you say about the magnitude of the momentum of the dart and the magnitude of the momentum of the Nerf gun after the dart is fired? It's going to be the same, right? So whatever momentum forward has to equal the momentum going backwards. So we've now established that the force, change in momentum, impulse are the same for both the Nerf gun and the Nerf dart. They're the same. That brings us to an important question. Why is it that you don't want to get hit with the dart, but the recoil from the gun isn't as bad, right? Why is that? So the big question is, why is momentum the full story, right? So we did this lab, is momentum the full story, in which we rolled these different objects down a ramp and saw how far that it pushed those cups. So you can look at these graphs, right? So we did this, we rolled it down 3 times, and you can see the graph. In the first part, we changed the mass, right? We changed different objects, rolled it from the same velocity, and you can see here that it pushed it at a certain rate. And then the next time what we did was we rolled that same object down the different notches and we changed the velocity. So these are the graphs that it generated. So let's look at some of these questions. So look at the mass versus distance graph. So that's the one on top. And the velocity versus distance. Well, how are they the same? How are they different? They're both going in a positive trend. I increase the mass and I increase the velocity. The distance that cup is pushed is going to remain this, or it's going to go up. They're different because one is a linear graph and the other appears to be curved. So I asked you to compare these graphs to the graphs down at the bottom, and you can see here that the mass is a linear graph, right? It goes up in a linear fashion. However, when I change the velocity, the the distance that the cup travels goes up in an exponential fashion. It goes up in an x squared. So that last question is like, if you wanted to push the cup farther, would it be more efficient to increase the mass or the velocity of the object hitting it? The answer is you'd want to increase the velocity, and it all has to do with the slope, because the slope of the mass versus distance line, it is a straight line. It's a slope. It's a constant slope. Now, the slope of the distance versus the cup push versus the velocity is exponential. It's always changing. That slope is always increasing. So whatever number you're trying to get to, it'd just be more efficient to increase that velocity than it would be to the mass, because it is an x squared relationship. So now let's jump into something. Does a rubber band contain a force, right? Does the rubber band contain a force? Does a rubber band contain a force if you bend it back, right? Does it contain it? What if I pull it back and point it at you? Like, would you flinch, right? What about a candy bar? Does it contain a force? What about a battery? Does it contain a force? You recognize that all of these objects contain something, but it's hard to say whether it contains a force. Now, here's the thing. You cannot possess a force. You can exert a force, but you cannot possess it. A force is a part of an interaction. It is not a physical entity that can be owned. Now, all of these things do contain something. It begs the question, well, what do they contain? I'll give you a hint. It begins with N and ends in a G. Energy. All right, just a little joke there. I'll give you some time to laugh at that one. Energy, right? Energy. That's what we're talking about in this unit. Now, energy is a very hard concept to understand. In fact, even Newton couldn't really wrap his head around it. He even originally wrote Newton's second law sort of in the perspective of momentum. He thought, hey, you know what? Momentum's got to be the full story. But other people started to see little discrepancies, just like we saw with the is momentum the full story uh, lab. Now let's just do a quick thought experiment. Describe the color red to me without naming an object or showing or pointing to anything. Pretend you're describing it to someone who's been blind their whole life, right? So if you're just describe the color red. Well, energy is a lot like the color red. You know it when you see it, but you can't touch it, taste it, hold it, smell it, hear it, or even really explain it very well. You just instinctively know it when you see it. Energy, like inertia, is something that a body can possess, but it's not something that's like tangible, something that you can touch. So here's another little thought experiment, right? So if you look at a brick, what two things could you do for this brick that cause you to fear for your safety? We could hold this brick over your head, or you could throw it at you, right? We call this ability that the brick has to cause you harm, either due to its location in a force field or due to its motion, called energy. So energy is the capacity to do work. Now, work is also a scientific term that we'll learn about in the next unit. So all forms of energy are scalar, which means it is only magnitude, no direction. So the unit for all forms of energy is the Newton meter, aka the joule, represented with a capital J. There are four basic ways of storing energy. You have potential energy, kinetic energy, internal energy, rest mass. So let's understand these different forms by making a chart. So we're going to make this chart, right? So this just helps me organize it. So uh, these are all different forms of energy. The gray, those are different types of energy that, yes, we'll learn about, but those are like different units, right? The other ones are going to be the ones that we're going to talk about. Now, red, non-mechanical energy. So this is just like what we need to be aware of. Blue is a mechanical energy. This is what we really focus on when we start calculating energy. And dashed lines are forms of potential energy, right? So kind of there's like some murky, but this is just a way that I like to keep track of all the energies we learn about. So let's just look at gravitational potential energy, right? So a rock falling, what gives it potential? What two factors determine how much potential it possesses? So what could you do to make that rock like hit harder, right? So gravitational potential energy is stored capacity to do work due to location in a gravitational force field. Gravitational potential energy depends upon three things. Number one, the object's mass. Two, the gravitational strength, and how high that object is raised. So mass times gravity times height, right? Now, the thing is, like the acceleration of Earth or gravity, right? We use that's 9.8 meters per second squared down. I like to use 10 just because that makes the math a lot easier. But that's the strength of whatever planet you're on. If you went to Jupiter, well, it'd be a lot more than it would be on Earth. If you went to the moon, it'd be a lot less. So let's just take a look at another form of potential energy, elastic potential energy. So it's stored capacity to do work due to location electric force field. So it's like stretching those bonds in something that's stretchy. So think about it this way, like what it depends upon is two things, spring constant, or basically what that material is made out of, or what material it is, and the spring displacement, how far back it's that or compressed it is, right? So it's not necessarily just stretching. It can also be compressing. So think about dropping a ball and it compresses, right? That's elastic potential energy being stored. So how could a ping pong ball hurt you despite its low mass, right? So think about that, right? So if you get it going fast enough, it's going to hurt you, right? So let's take a look at that last kind, right? The kinetic energy. The energy due to motion of an object is defined as kinetic energy. So what two factors determine how much kinetic energy something possesses, right? So what would hurt somebody more if they were getting hit with like a ball? Well, if you increase the velocity, increase the mass. Now, kinetic energy depends not only on the velocity of the object, but also its mass. Now, you might be thinking, isn't that just momentum? Momentum equals mass times velocity. True, but it turns out the velocity plays a bigger role in kinetic energy than it does with momentum. And you can see that in that equation there. Kinetic energy is 1/2 times the mass times the velocity squared. Now, we saw that in this lab. Notice that when we increased the mass, it went up in a linear fashion. If you look at that equation, 1/2 times mass, well, nothing's happening to mass. It's not squared, it's not square root, it's not log, it's not anything. It's just linear, right? And the velocity is squared. So we saw that. That's what we were measuring in that Is Momentum the Full Story lab. We were measuring the kinetic energy. That's what was pushing that cup, the energy in that cup. All right. So now let's get to other forms of non-mechanical energy. Chemical potential energy is not a type of potential energy, not mechanical energy. Chemical potential energy is energy stored in the electrical bonds between atoms. So this type of energy is that's stored in the foods that you eat, gasoline in your car, and the batteries in your phone. This type of energy is a chemical reaction. It's mostly focused on in a chemistry class. Just be aware of what it is. So basically, we're breaking those electric bonds. So the food that you eat, that's where you get your energy. Gasoline in the car, that's what makes it move. Batteries in your phone or anything like your remote control, chemical potential energy. So let's answer this question. Why can you safely stay in a sauna even though it's at a really high temperature? So think about this one. Saunas usually operate between 180 and 195, right? But they can go as high as 220 degrees. Water boils at 212, which begs the question, could you keep your hand in boiling water as long as you could stay in a sauna? Here's another thought experiment. An oven has a temperature of 450 degrees. Have you ever opened the oven after cooking something to have that air hit you in the face? Why doesn't it completely burn your face? Now, there's something else out here, right? So let's just say that the air hits your face. Now, if you reach your hand in and grab that metal rack inside the oven, it's going to burn you. They're both at the same temperature, but one is just a mild inconvenience. You take a step back, and the other would seriously burn you. So that brings us to internal energy. Internal energy is the combined potential energy and kinetic energy of the atoms and molecules stored in an object. Temperature is not directly proportional to internal energy, and we'll go over an example of that. But since temperature measures only the average of translational kinetic energy, part of the internal energy is the total amount, right? Two objects with the same temperature do not necessarily have the same internal energy. I like to think of internal energy as how much is that substance? How much energy can that substance store? Like all the spaces that it can store. So you can see here, just like the systems with the same temperature, gases can't really store a lot of energy. Liquids and solids can store a lot of energy. So that's why when you open that oven and that hot air hits you, it doesn't really have a lot of energy. The temperature is high, yes, but it doesn't have a lot of energy that it transfers to you. Now, the solid rack or like boiling water, it does. It has a lot of that energy and it can transfer it to you really quickly. So here's another one, right? An oven, 450 degrees and boiling water at 212, which has a higher temperature, that oven, right? Which has more internal energy. Well, it's going to be that water, right? The oven has a higher temperature while the water has more internal energy. This is why you can momentarily place your hand in the oven, not be worse for wear, but the same is not true for boiling water. So let's look at a cup of hot water and bathtub filled with tepid water, which has a higher temperature. Well, it's going to be that that cup of water has a higher temperature, but the bathtub has more internal energy. It would take more energy to boil that water, right? Even like that's where it can store all of that energy. That's just an example. Internal energy versus temperature, right? They sort of go hand in hand, but they're not like something with a higher temperature doesn't necessarily have more internal energy. Why is it easier to stand in the cold air than jump into cold water even though they're at the same temperature? Well, it does have to do with the fact that yeah, you're standing outside in the air. The cold air outside, like it doesn't have a lot of places to store that energy, that internal energy. So it can't really take that energy away from you that quickly because it can't really store that energy. Now, if you jumped into water, now that's a different story. Water has a lot of places to store energy, and it's going to take that energy from you really quickly, and that's the difference. Even though they're at the same temperature, right? You step outside, Yeah, it's a little cold out. I can still be out in a t-shirt. You fall into water. Well, that's a different story. Same temperature, but the internal energy is what makes them different. How does the sun keep generating its energy? That brings us to our last form of type of energy, rest mass, right? What does it mean to say something has rest mass? This is Einstein's famous equation. I know all of you have seen it before. E equals mc squared. Rest mass is the energy stored in the mass of all matter. So nearly all energy that you will interact with in your life originated from the sun's converted rest mass. So geothermal and nuclear do not originate from the sun. Every second, the sun converts 600 million tons of hydrogen per second. Oh, yeah. For comparison, the mass of the Earth is 1 times 10 to the 21st tons. This would mean that the sun consumes a mass of Earth every 70,000 years. So it's just converting the mass into energy. Just the fact that energy, uh, just the fact that yeah, like it has mass. Uh, it is energy, right? Mass is energy, energy is mass. That's what Einstein showed, that you can go back and forth with his equation equals mc squared. A lot of energy is stored in mass, right? So we think about nuclear bombs. So on August 6, 1945, 66,000 people died instantly at the Hiroshima blast. Just as many people died later due to severe burns. All of this death and destruction was caused due to rest mass. Now, the bomb at Hiroshima only converted 700 milligrams of mass. That's only 1/3 the mass of a dime. Einstein was against dropping the nuclear weapons, and when he heard they were dropped, he is quoted as saying, "Woe is me," right? He was not allowed to work on the Manhattan Project just because he really, he didn't agree with using the physics to make them. Now, Oppenheimer, who is known as the father of the atomic bomb, is quoted as saying, "Now I am become death, the destroyer of worlds," when he saw the detonation of the first atomic bomb on July 16, 1945. We now have bombs over 3,000 times more powerful than the Hiroshima bomb. So, very powerful stuff dealing with rest mass, the energy due to an object's mass. So here's our energy chart filled out. So you can see here, the gray ones are ones that we can deal with a little bit later. The red ones are the ones just to be aware of. Now, mechanical energy, that's the one that like we really focus on when we start to calculate the energy. And we'll go over what makes those so special. So this is the total energy chart filled out. And so once again, oh, sorry. Now, last thing we want to talk about is why energy. Why do we need energy? What can energy do that momentum cannot? So in order to answer this question, we did collision carts too. Now, we've already done this lab, and we did the exact same scenario, except instead of calculating the momentum, the total momentum of both carts before and after each collision, we calculated the kinetic energy of the combined cars before and after the collision. Now, what I want you to see here, though, is notice that the kinetic energy is not the same before and after, right? So these are the questions that I ask you. The total combined kinetic energy isn't quite the same in all of these scenarios, right? They're not quite the same in all of them, right? Now, momentum, it was. Now, momentum is conserved, which means it cannot be created or destroyed. Look at the total kinetic energy before and after the collision, all four simulations. How is energy similar to momentum? How is energy different? Use the data to justify your answer. Well, notice that the kinetic energy, isn't conserved in all of them, right? In my inelastic collision, I've got 50 before, 12.5 after. My elastic, well, great, I have 50 before and after the explosion. I actually have more after the collision, right? So something's going on here. And notice there's no negative numbers because energy is a scalar quantity while momentum is a vector quantity. So you don't have negative equations. Look at the simulations for elastic and inelastic collisions. In terms of kinetic energy, define elastic collisions and inelastic. So let's go back to that last one. Here, my elastic collision and inelastic. In an elastic collision, the total kinetic energy is conserved, before and after the collision. In an inelastic collision, it's not. It's less than that. Now, look at the first explosion simulation. What is the total kinetic energy of both carts combined before the explosion? What is the carts? The carts are in motion after the explosion, which means they have kinetic energy. Where did this kinetic energy originate? And I give you a hint, what caused the carts to move? That explosion. The explosion caused it. I started with zero kinetic energy. There was an explosion, and I do have kinetic energy after the collision. So momentum can be transferred from one object to another. Look at the elastic collision simulation. Can energy be transferred from one object to another like momentum? The answer is yes, right? The answer is yes. So if we look at that elastic collision, I have 50 joules of kinetic energy before and after. Well, look what happened, right? What happened was that red cart transferred all of that kinetic energy to that blue cart. So yes, just like momentum, energy can be transferred. So that brings us to that last question. Energy, like momentum, is conserved, which means it cannot be created or destroyed. Does the data support this? Well, looking at the simulation, no, right? It doesn't, like the kinetic energy before and after the simulations are not the same. Does the data support? Let's see, there's one thing that can be done to energy but cannot be done to momentum. What can energy do that momentum cannot? So I give you a hint. How many forms of momentum are there? We just learned about one, mass times velocity, right? How many forms of energy do we learn about? The only thing I had you calculate in this simulation was kinetic energy, right? Not other kinds of energy. So what's happening is, think about that explosion. I started with zero kinetic energy. That explosion caused it to have kinetic energy. That energy originated from the chemical potential energy inside of that, like the original explosion, right? So what energy can do that momentum cannot is it can transform and change into other forms of energy. And that's what was happening in this. So that brings us to the law of conservation of energy. The law of conservation energy states that energy cannot be created or destroyed, only changed or transformed uh, into one, or transferred from one object to another, right? So in other words, like momentum, energy cannot be created or destroyed. It can be transferred from one place to another. Energy can also transform or change into another form of energy. Now, I like to think of while momentum is like money in the room, it can change hands, but the total amount remains the same. I like to think of it as energy as like somebody that's backpacking around the world, right? So they're going to have to convert their currency into other forms of currency, but overall, their total buying power doesn't really change, right? So they still have the same spending power, but they have lots of different currencies. They can change it to different forms of currency as they travel. All right, so that brings us to elastic collisions, right? So we already learned about elastic collisions in terms of momentum, right? No lasting deformation, no heat generated, no sound. Objects tend to bounce off each other. Now, there's no such thing as a perfectly elastic collision. There are things that are close. So in terms of energy, an elastic collision is a collision in which there is no net loss in kinetic energy in the system as a result of the collision. So what that means, and we saw that in the simulation, all the kinetic energy before is kinetic energy after the collision. I have no loss to energy to the outside world. Now, in an inelastic collision, right? Remember, there's permanent deformation, generation of heat, generation of sound. Objects tend to stick together. Now, almost all collisions are partially inelastic because collisions do not conserve another quantity known as kinetic energy. So in terms of energy, an inelastic collision is a collision in which kinetic energy is not conserved due to the action of internal friction, right? And I'm losing energy to the outside world. Think about bouncing a ball. You can hear that ball bounce. That energy had to come from somewhere. It came from that kinetic energy. That's where it originated. So just as a final thought, remember, there is too much unknown in the universe to take a break from learning. Get out there and question everything.